Hey, hi everyone. We'll get started now. We'll just give a few minutes for people to join. Thank you all for joining us today. We're going to cover a session on oil diagnostics for data-driven asset health. So how we can use the information from oil diagnostics to really help you look after the assets and understand the health of those assets. So just before we get started, I'll introduce myself. So I'm Jonathan Lewin. So I head up the HV monitoring business, and I'm here with John Joseph, who heads up our oil diagnostics laboratory. So little brief background for those of you who don't know who we are. So been around for an awful long time, 1966 onwards. In 1994, we became who we are today, EA Technology. We were the research centre for the government, and then we essentially went privatised when the industry went privatised as well. So fast forward to the present day, 2024 and beyond, we're really a company who facilitates the transition to net zero. And that's where a lot of our kind of propositions and work and involvement with our clients sits. So what we do essentially is we turn monitoring stuff into insights, and it's all about collecting data, using data about how we create safer, stronger, smarter networks, and ultimately how we keep that power on to our homes, the factories, plants, things like that we need to survive in the modern day. A lot of the stuff we do in the condition world is to prevent catastrophic failures and to prevent any financial losses associated with that, and to create kind of clarity around kind of asset investment decisions and to really provide that information to our client base. The global reach company, we have places in the US, obviously UK, Australia, Singapore and China. So all the services we offer span out across the globe. So before we jump into the oil sections, I'll just give you a little touch point on some of the recent developments that we've done in data collation for both PD and oil. So a lot of you will be familiar with the UltraTev. Not going to go into that in any detail today, but essentially there's been a recent release and update of that product. And as you can see down in the bottom right there, there's another update coming soon in terms of the UltraBulk. If you want to know more about that, there's a slide in a couple of ones that show you the webinars that were done previously on those. So recent upgrades on the UltraTev is looking at the flexible surveys. So essentially we've added asset classifications, which give you an ability to have the appropriate asset class and the appropriate survey structure for that particular classification that you're serving. There's also an AI data-driven analytics in there and some advanced analysis in terms of time frequency TF mapping. Again, they're all covered in a previous webinar that my colleague Gareth Devine did. So if you want to look at those, jump on the webinar after this and have a watch of that. So they're the 3 webinars that were done in the TEV series. Again, you'll get a copy of this, so you can jump on those after this one if you've got time. So from a laboratory point of view, we've recently expanded our laboratory. So this is obviously what we're here to cover today. So the whole point of doing the oil analysis is to provide that early fault detection. It's essentially the blood sample of the electrical oil field assets. The laboratory itself, we deliver about 40,000 samples a year. So we do a lot of this kind of work across global network operators, large scale kind of international industrial clients, rail industry, renewables, service providers, you name it. We pretty much cover that from an oil point of view. The renovation work is due to complete in the next month or so, and it's essentially will allow us to double our capacity up to about 80,000 samples per year. So that just kind of sets the scene of where we're up to date. So the next section is covering off kind of some baseline fundamentals on oil and why we do it. I'm going to pass you over to John Joseph, who is going to take it from here and run you through those this kind of next section.
Okay, so fundamentals of oil diagnostics. So why is oil diagnostics important? Well, it's a really good tool for looking at the condition of your oil field assets. I'd also suggest it's a very cost-effective tool for doing this. And based on the information garnered from oil diagnostics, you can plan your asset management strategies based on accurate determined information from that asset, and accordingly plan your maintenance schedules, any intervention to prolong the life of your asset, and also plan your asset replacement in a timely manner. Also, if you're going to handle any oil field asset, whether that's during maintenance or replacement or investigatory work, you want to know what you're handling to make sure you're doing it safely. So for that, you want to know, are there any polychlorinated biphenyls, PCB risks associated with those older assets? Is there an explosive risk? Is there a high buildup of combustible gases inside that asset? Are there any other hazardous materials in there, such as heavy metals, for example? Also, through oil diagnostics, we can identify faults present in the asset. We can monitor those faults and also encourage intervention before failure of the asset occurs. And clearly, preventing failures saves money for asset owners, both in terms of the cost of replacing those assets should they fail, but also the avoidance of downtime as well on the network. So in terms of the oil diagnostic process, here's a quick diagram showing the key steps involved in that process. So it starts with sampling of the asset, so taking fluid out of your asset in the field, putting that sample into a crate, shipping it to the laboratory. At the laboratory, that sample is then registered into the OLIMS system, Laboratory Information Management System, the appropriate tests, passed through to the analysts. They undertake the laboratory tests that are required. That then goes through reporting, where the results are reviewed, and a report is produced with recommendations based on the results from that analysis. One of the biggest issues we see as a lab, I'm sure it's industry-wide, is data transcription. So obviously the site guy goes to the asset, he reads that nameplate on there, serial numbers, manufacturer, some of those nameplates are very old, hard to read. That's then transcribed from the nameplate through to the sample label. From there, that's sent to the laboratory, where the registrar reads that information, registers into the system. Any point there could be a transcription error in that. Is that a 5? Is it an S on the serial number? And other issues can arise. And how we propose to address that, something that we'll come on to later in this presentation. So when it comes to sampling with oil analysis as a laboratory, what we're doing is determining the condition of the oil in that bottle that's sent to the lab. As such, it's imperative that the condition of the oil in the bottle is representative of the condition of the oil inside that asset. How that's done is by ensuring a good quality sample is taken from the asset. So that involves a suitable flush of the pipework to make sure any debris, residue, moisture present around the valve is flushed out before the sample is taken, at least a litre out of the asset. Make sure the actual sampling equipment in a bottle is also flushed to prevent debris buildup in there, condensation, and other issues as well. One of the biggest causes of poor fluid quality when it comes to low breakdown voltage strength or high moisture is poor sampling technique. So with oil analysis, there are 3 main pillars to that. So that is your operational status. So how is that transformer operating in service? That's determined through dissolved gas analysis. You then have your fluid condition, which is your routine analysis, predominantly moisture testing, acidity, and breakdown voltage testing. So what's the condition of that fluid in the asset? And then finally, what is the health of that asset today? And that's looking at the condition of your solid insulation, your stainless paper on the windings through Furan testing. So in a bit more depth now, looking at the operational condition of your asset, dissolved gas analysis. As a lab, we test for 9 gases. Of those, the fault gases are your hydrogen, methane, ethane, ethylene, and acetylene. So as a insulating fluid in an asset is exposed to thermal stresses, characteristic gases are generated within the oil, and which gases are generated are characteristic of the temperature achieved during that activity. So by looking at these gases through dissolved gas analysis, we can garner a good understanding of as to how that asset is operating in service. So typically, at lower energy, lower temperatures, you get hydrogen produced. That's characteristic of partial discharge, along with low levels of methane. Your heating gases, they are methane, ethane, and ethylene, and that's as your temperature increases in there. And then it comes to arcing, you're looking at acetylene being generated along with low levels of hydrogen. And the interpretation guidance for dissolved gas analysis is predominantly IEC 60599, as long as the IEEE standard as well, where there's no history to review. Here are some pictures of activity. So the top image there is an example of treeing on a insulation board due to partial discharge. That's the gradual erosion of the insulation material. Once enough of a path's been created, a flashover can occur in those instances. The bottom image there, that is two windings from a transformer stripped of the cellulose paper. Those two pinholes you can see there are where an arcing event has happened between the two windings. That's very high temperature, very destructive to the winding itself. As you can imagine, the paper as well in that area will have been completely destroyed in that process. So when it comes to interpreting the dissolved gas analysis, historically we used to use limits, similar to what we do today, to fluid condition. We moved away from that, and now we're looking at trending rather than absolute limits, and that's the guidance given by the IEC. What we can see here are two transformers, so TX1, TX2. These are actual transformers, one of which failed in service. We've got oil history here over a 10-year period, so from 2006 through to 2015. TX2 at the bottom, you can see particularly for the methane and the ethane, taking the IEEE limits over the 10-year period, that transformer is consistently above the limit for a flag. But very, very stable, so no issues there. When it comes to the top transformer, what you start to see is low temperature heating gas, methane, appearing in there. Over the years, you've got a fault that then progresses from low temperature heating to higher temperature heating. When you look at the full data available for this asset, actually you have got PD activity before this that then becomes a heating issue, high temperature heating issue, arcing issue, and then ultimately that asset did fail in service. So that's an example of how taking absolute limits can give a false impression as to what's happening in that asset. So moving on now to the fluid condition, this is the primary driver for maintenance on an asset. So historically, assets are often maintained on time-based intervals, which led to a lot of assets being unnecessarily maintained prematurely. These days, you want to drive that maintenance schedule based on the actual condition of the fluid within your asset. So when it comes to fluid condition, the three main tests we're looking at is moisture content. So what is the water content in that oil? If you've got high moisture, you're going to reduce the dielectric strength of that insulating fluid and also accelerate the degradation of the paper in that asset. It's important to note that within a transformer, approximately 90% of the moisture is held within the solid insulation in the paper. As the temperature increases within the asset above ambient, above 20, you start to see increasing migration of moisture from the solid insulation into the oil itself. For that reason, we do ask for a measurement of flowing temperature of the oil at sampling, so we can then correct those fluctuations and look at a consistent temperature corrected value for trending moisture over time. That's important to determine whether you've got a high moisture due to internal degradation of the asset or whether you've got a moisture ingress issue in the asset, and the correct actions then will depend on the cause of that high moisture. Next up, we have acidity. So how acidic is that oil in the asset? The oil naturally, it does oxidize with age and it becomes increasingly acidic. What you don't want to see is that progress into sludging in the asset, because that will be catastrophic for the asset itself. When it comes to acidity, you want to treat that before sludging occurs. The higher the acidity, the higher rate of degradation you'll see on the internal components of your asset. Again, particularly the papers within your transformer. And finally, breakdown voltage strength test. That's looking at the dielectric strength of your fluid in your asset. What affects your breakdown strength? It's high moisture content or contamination within your asset. When it comes to guidelines for interpreting those results, that's IEC 60422, and there's different thresholds based on different asset categories and types. So all these factors, whether that's high moisture, high acidity, or contaminants within your asset, that will accelerate the degradation of your solid insulation, thus reducing the expected lifespan of that asset. The idea is you undertake remedial action to then prevent that accelerated degradation from occurring. One thing to bear in mind when it comes to maintenance is the risk of data loss. So here you've got a set of results from an asset from an oil test. You can see here there is evidence of high temperature heating, really elevated ethane and ethylene particularly. Also slight arcing is noted there with the acetylene. You have got very high acidity, so 2.9 on the acidity. You've also got moderate levels of FFA present in the oil. For engineers out there, a FFA result of 1.1, it's a DP of low 400s, maybe about 420-ish, I'd suggest on that. So say you take that result and you intervene, so you replace the oil in your transformer to remove the acidity. You retest the oil, everything now comes back fine, but it's not fine. You've treated your acidity, that is now sorted. At the same time, you've stripped out all the markers evidencing your high temperature heating issue, and also your marker for paper health. Obviously, you've not fixed your potentially loose contact in your transformer. You've not healed your paper, you just stripped out the evidence as to what's going on there. That's not saying maintenance is wrong, something to be mindful of. What we'll find over the course of the months and the years, that will re-homogenize in your asset. So 12 months later, you're starting to see those heating gases reappearing, but your furanic compounds haven't quite returned to the level which is indicative of the actual paper health within your asset. It is important when you do treatments, let the lab know that's been done, otherwise we could give a false diagnostic. So we might test the asset, see high temperature heating, treatment's done, we get another sample a year later, we think the heating gases are stable, when actually they've been stripped out and they are still rising, so the fault's still active. So the final pillar, so we've done operational status, we've done fluid condition, is the solid insulation condition. So within your transformer, your solid insulation, your cellulose paper applied to your windings is the critical marker of asset health. You can do a lot on an asset, you can't cost effectively repair and replace paper within your transformer. So for new cellulose paper from manufacturer, you have what is called a degree of polymerization, so measure the cellulose chain lengths of about 1,200. That paper is then wound around the windings. That winding process will pull that DP down to about 1,000. So that's at the point of insulation within your asset. Then over time, due to a combination of factors, so pyrolysis, that's heating of the papers, oxidation, so reaction with oxygen, and hydrolysis, reaction with moisture, that paper will naturally age and degrade within your asset down to the point of about 200 dp, which is classed as end of life. The paper basically goes from new oven grease-proof paper to grease-proof paper that's been put in the oven and overheated and burnt and crumbles in your hands. At that stage, any abnormal loading on the asset, the paper will crumble off those windings, which is like 200 dp is classed as end of life. When it comes to lab, what we look for is the furanic compounds. So these are compounds that develop in oil as the paper degrades in the asset. And from the perfluoraldehyde, FA or 2-fal, all named the same compound, we can estimate the health of your paper within your transformer. As a side note, PCB testing, so polychlorinated biphenyls are a carcinogenic compound which can be present due to contamination in oil of particularly older assets pre-1986. Right now, there is a requirement for any asset owners to have any asset of PCB content above 50 parts per million to have that off the network by the end of this year. So there's a big driver now to do those tests to determine the PCB fluids of the assets. Current regulation, anything with PCB content less than 50 parts per million, that's classed as non-PCB transformer. Between 50 to 500 parts per million, that's PCB contaminated. Anything above 500 parts per million has to be removed from the network at the point of getting that determination on that asset. So when it comes to reporting the results, there's a few different layers of depth we can go into with that. So you can do a basic investigation. So you take your asset details, you do your fluid quality test, your dissolved gas analysis, and your papers, and from that you get a basic report saying this is the current state of your asset. It's perfectly fine for fluid condition because the measurement of your moisture, your acidity, your breakdown, water strength, that is an absolute determination that will drive your maintenance schedule. The next level slight is taking historic data, predominantly historic gas results, but also any other history you have, and using that to make a more holistic judgment as to how that asset is operating in service. So that's trending data over time rather than taking individual measurements. Going another layer down from that, you've got your diagnostic analysis. So this is more in-depth laboratory testing. So dielectric dissipation factor, interfacial tension, particles, corrosive sulfurs, a whole look of other laboratory tests that goes to the next level of determining what is the condition of that oil and what action is needed. You can also do a full health index assessment, which we'll come on to in the next section. That's taking not just the history, not just the fluid based on lab results, but also the asset age and other data to predict where the asset's end of life is. When it comes to reporting, it's important that those reports are clear and concise and give accurate recommendations to asset managers that have to, next steps on that asset. So that should detail asset information, the oil results, the history, comments, and the statuses on those. So now back to Jonathan to talk about Transformer Health Index.
Okay, so obviously, before we kind of move on to the next section, a lot of information there just on the general type of oil stuff that we do. Any questions, chuck them in the chat. If we can't answer them at the end, we'll make sure your responses get to all the questions that are put through. So now we've done all that testing, we've got all that data. So what's next in that? So the next phase of program that you can then look at is kind of the health index platform. So a health index platform takes all that condition data that we've just discussed from the operational condition, the solid insulation condition, and the fluid condition, and it groups them together to be able to look at and understand asset monitoring, asset maintenance, so life enhancement measures, and asset replacements. And it's a very powerful tool for kind of site-wide application. So essentially, to get the most out of that data, what you need to start doing then is you're not just looking at an asset in isolation, you start looking at it from a site-wide program. So you look across the base, you look at all the assets at a particular facility or location or area, and start to understand the health in relation to each other. And by applying something like a health and looking at it in that way, you start to be able to rank those so you can see your best case assets and your worst case assets in terms of proximity to end of life. So by understanding the degradation of the oil and the failure processes behind that and taking those detailed results, as well as some other results, you can then start to profile that fleet, if you like. So when we're looking at that, we have those health indicators from the oil that we're looking at. We take asset information, so age, location, is it close to the, is close to the sea, so it's got higher corrosion rates. Is it indoor? Is it outdoor? Is it got a lot of industrial pollution? What's the loading, both now and in the future? By gathering that information fairly quickly, you can start to not just assess what's going on with the oil, but you're pulling in other asset condition data and factors into that. And that gives you a much more rounded and robust way to understand what's going on with that particular asset, but as I said, across the asset fleet. So when we add then into things like visual condition, have you got any leaks on there? Is it rusting, damage, vandalism, etc.? That all goes into adding into that program. And you combine all that data together. The health index that we do is essentially the data methodology and algorithms of our CNI models, which is what Ofgem essentially uses as part of the regulatory program. So it's a quick little snapshot into that world that can be done just based on the oil stuff, separate from a large application process. So once they're ranked 0 to 10, 3.5, kind of 4 below, okay, green, happy with that. 3 to kind of 7 or 4 to 7, moderate. So they're the ones that you're going to look to take intervention on. So it provides that data, that understanding of where to put your maintenance budgets and what assets are at higher risk of failing and therefore taking power out to your plants, which can't drop off power. Anything 7 above, typically you're looking at end of life. You can bring those back, but it depends on what's wrong with them. So you end up with a health index kind of probability curve. At the higher end down there to 10, you can see how that curve goes up, but it means that the probability of that asset failing is higher than if it was a low health index, say of 3 or 2, which is nice and green. It's got a much lower probability of failure at that point. So when you're looking at it from a site-wide perception, you can then start to understand your current condition, your probability of failure of all that, and the 10-year estimated condition. And from that, we can then understand the proximity to end of life in number of years. Clearly, that's an estimation because, it's in the future, but it gives you a good understanding of where to start to prioritize some of this across fleets of assets. So here's 2 graphs taken from a profile. So the one on the left is the 0-year profile. So that's the current profile based on your results to date. In 10 years' time, the expectation is that that profile will degrade and will naturally move to the right-hand side image. You can see there's more oranges in there, more reds, which are costly exercises to fix. So if we don't do any intervention, that's what happens. But what we want to be able to do, and what this provides you, and by harnessing that data from the oil, it allows you to put the correct interventions in place to pull that data, or that asset, and that transformer back into a healthy green state, which provides a safe and reliable condition. So it prevents any of those costly replacements and enables actions to be taken before they become a serious problem on your critical infrastructure. So the other things you can add then, you can add other asset health indicators. So you can do PD survey, monitoring data feed-in, thermal surveys, and any other asset data systems can go into there. So there's a whole lot of different stuff that can go into asset health and asset condition. But essentially, the top 3 that we covered are the ones that we need from an electrical transformer with oil in it. They're the ones that drive the majority of that work. So that's one part of it. So the next phase of how you use that data is our OLIMS platform or similar platform. So this is a kind of a sneak peek, if you like. So this is a system which is about to go live in the next couple of weeks to months or so. And it enables us to digitalize the process from end to end. So by doing so, essentially, what we are doing is taking that data, centralizing it all into a platform, and allowing then a client portal view into that platform. So clients can essentially log in and access all this data that we've been talking about. So instead of it just being written down on a piece of paper, on a PDF report, which gets filed away, it's in a system at your fingertips where you can then derive better value from it. We've got a couple of videos just showing you how that works, which we'll come on to in the next slide or two. So essentially, the aim of this is to monitor the asset health across fleets of assets. So if you have one particular site, the data's there. If you have multiple sites or networks, you can essentially visualize all that data in one place and start to get a holistic view of what's going on across that network, whether it be a large DNO kind of network or whether it's an industrial specific network. The whole point of what we do with the system is to improve the data integrity. So the oil data is great, and between us and the people in the field doing the sampling, we can make sure the quality of that data is where it needs to be. But essentially, what we then need to do is look at the actual physical data itself. So that's kind of like your metadata, if you like, your asset data. A lot of the problems we see is, as John said earlier on, is from that labeling. So there's 90% of that is improved through that digitalization process. So we improve that integrity of the data. So that's pretty much what we've got to cover. We are hosting an industrial forum, which we do most years. So this time it's bigger and better than ever. So if you're interested in the theme of keeping electrical switchgear safe, or you're an industrial player or interested in that area, we've got this thing on the 14th of October at Chester Racecourse. So you can sign up for free, come on down, and we'll all be there to welcome you. It should be a really good day. At the same time, we've also got the Power Skills Conference. So same place, same time. If you're interested in training for future engineers and developing that training set skills, then that's the place to be. So thank you all for your time. So what's next? So any questions we've got, we can answer for you if they're on there. So I'll jump onto the Q&A tab just so hopefully I can read these out. So first one from Tom. Can the OLIMS system also be used for PD, thermal, ETC testing and data analysis and trending over time? So in short, Tom, the answer to that is no. However, we have another system which is called managed surveys. So that basically does the same thing for PD data. They're both built on the same 360 platform. So the data is all held in the same place. And part of our software or our platform integration piece going forward is to point those two as a centralized function. But as today is there are two systems which collate data. So the PD data is collated from the UltraTev, and the oil data is collated in a similar way, but two slightly different platforms. So we've got another one in from Jack Croden. Is the digitalization software used the same as VisNet for load monitoring and alarms? It's not. It's a different software. Again, it's built on the same platform model, but the OLIMS is specific for the oil data platform. It's built as a laboratory tool, basically to support our view and to give more oil data information. What it does, that will then do, is it can then feed into kind of asset investment software platforms and things like that. But the VisNet is a different software tool, but built again off the same eco structure, if you like. So hopefully, Jack, that answers your question. So we've got another one from David. When sampling outdoor oil-filled assets, how detrimental can poor weather conditions be to getting accurate sampling results? Would you recommend postponing sampling for a day with better weather conditions? So in an ideal world, yes. Obviously, depending on where you are in the world, in the UK, that can be very difficult to do. It's key, like with that sampling page that we touched on, the absolute key thing is to protect the bottle. So the sample kits that we use as a laboratory basically is a closed system. So what you don't want to do is just open the bottle cap, have it open to the elements, and then take a sample, because you'll be getting rain in there. You only need a small little bit in there to affect your results. So in short, if you can do, yes, but in practice, that's not always feasible. So it's about using appropriate sample kits, and if you can, have a protective way to cover that sample port, so you are protecting that bottle as best you can. So another one from Reese. Do you have experience in DJ analysis for natural ester systems? If so, have you ever seen evidence of outgassing in newly installed fluids? Essentially, yes. So we do oil across all different fluid types: natural esters, silicon, cable oil. It depends really on the application. To be honest with you, they can gas. You get a lot of issues in things like renewables. So typically when it's gassing, it's because there's a reaction going on with the internal components. So if you look at like a renewable space, they purchase particular types of transformers that are fairly cheap, that they want to last 25 years. And sometimes the internal components don't like the oil or the midel or the ester that's in there, and it can cause gassing reactions. So there's a discrepancy between that. Typically, you see it in ethylene. So if you have a massive, massive peak of ethylene, there's a good chance that's to do with a stray gas phenomenon rather than a heating gas issue. But it really depends on that application. So another one from Hamit. There is a new oil which is FR3, which is a biodegradable oil and marketed as better physical properties to other oils. Do you have much experience with this oil, and how does these parameters indicate as our fault change? So yeah, manufacturers will always say that their fluid is better than another one. FR3 is one that is used. We do FR3 testing. The problem you have with the newer fluids is because they are new. So you don't have the same level of data. So if you look at like a mineral oil, for example, mineral oil has been around for a very long time. There's a lot of information about it. There's a lot of IEC methodologies. There isn't the same methodology for the newer fluids. They will come in time, but as it stands, there isn't. So the best thing to do when you've got an FR3 is you use a similar kind of application, but the gassing's different. So interpretation will be slightly different depending on the fluid type. So when we're doing the interpretation on every single, the sample label, the report, it's all to do with the type of oil. So when we've got that type of oil, it's looking at that and understanding, are they any better than minerals? It depends. It depends who you speak to, depends on the application. You know, we have assets that are 60 plus 70 years old with mineral oil in and they're still going strong. It depends on the asset quality as well as the oil quality that you've got. So just lastly then from Andrew, what about DBDS results above limits impact to the asset? So essentially, yes. So DBDS is a sulfuric compound. So if you've got corrosive sulfur, DBDS is typically what you test for. The application to that is to add passivator to reduce it. The whole point of that is that kind of reaction and causes issues with your copper and your windings and things like that. So there is without going into a load of detail in the time frame that we've got, but ultimately it's about maintaining an acceptable level. If it's there, it's there. You have to have a passivator to keep that DBDS as low as you can. So essentially it passivates it, so it makes it become non-corrosive. So it's kind of like a bit like a neutralization agent. So hopefully that covers off all the questions we've got. If there is any more, like I say, send them through, and you know, we're going to make sure that they've all got a written response to them anyway. So I think that is probably everything. So thank you very much for all your time, and those of you who have managed to stay to the end, thank you very much for hanging in there. Like I say, anything that you want, any conversations or support that we can offer, if you're interested in any of the other webinars or the events coming up, just give us a shout, get in touch, and we'll make sure someone helps you out. Thanks all.
Thank you all.